Quantum mechanics is not restricted to the microscopic domain. It applies to everything, including human beings, galaxies, and physical objects we interact with daily. When a solid object strikes another surface, the matter does not pass through itself. This everyday rigidity is a direct consequence of the Pauli exclusion principle, a purely quantum mechanical rule. Despite this, we still teach atomic structure using classical analogies. The most persistent is the Bohr model of the atom, which depicts electrons traveling in distinct circular tracks around a nucleus. This planetary model relies on a strict classical assumption that at any given instant, we can pinpoint the exact position of the orbiting electron relative to the nucleus and simultaneously map the direction of its trajectory. But the math completely invalidates this picture. If an electron moves in a circular orbit at a finite distance, calculating the cross product of its radius and momentum generates a non-zero orbital angular momentum. Yet we know the ground state of a hydrogen atom has an orbital angular momentum of exactly zero. An electron cannot be in a state with zero angular momentum while also traveling in a uniform circular orbit. Because the electron cannot simultaneously possess the defined position and momentum required to form a trajectory, the classical concept of particles traveling along physical paths is completely invalid at this scale. To understand why paths don't exist, we have to look at this diagram of a classical phase space. It plots position on the horizontal axis and momentum on the vertical axis. In classical mechanics, a system state is a precise coordinate point. As time evolves, it traces a continuous trajectory line. Placing a definite point here requires knowing position and momentum with infinite precision. When applied to microscopic particles, nature mathematically forbids this simultaneous accuracy. The precise point diffuses into a fuzzy, vibrating region, completely erasing the possibility of a continuous trajectory line. This happens because position and linear momentum are what physicists call canonically conjugate variables. In classical mechanics, their Poisson bracket equals exactly 1, which intrinsically wires them together as pairs that resist simultaneous measurement. Without exact points in phase space, the entire predictive framework of classical Hamiltonian mechanics breaks down. To extract physical data from these systems, we have to abandon phase trajectories and build a completely new operational toolkit. That toolkit begins with Werner Heisenberg. His uncertainty principle is the fundamental law governing our fuzzy phase space, not a statement about the limits of human technology. The word uncertainty is a semantic failure of the English language. It implies a lack of resolution, the error margin of a microscope or a physical ruler. That is incorrect. In quantum mechanics, the delta symbol attached to position and momentum represents a rigorous, intrinsic statistical standard deviation of the system itself. This equation shows the formal definition of that standard deviation. It calculates the variance derived from taking an infinite series of measurements of a given state. It is a strict operational metric. But to calculate a standard deviation, you must first have a defined probability distribution to measure against. The primary objective of the quantum mechanical formalism is to provide the mathematical machinery necessary to generate those precise probability distributions. The fuzziness of a particle in phase space is not random chaos. It is highly structured statistical variance, and we need a specific equation to decode it. That equation was developed by Erwin Schrödinger. It replaces the autonomous Hamiltonian system as the engine of our physics. If we look at this flowchart, we can map the old classical pipeline directly against the new quantum pipeline side by side. The classical path feeds a Hamiltonian into Poisson brackets, which calculates a phase trajectory.
Since trajectories don't exist here, that path is a dead end. On the functional quantum path, the Schrödinger equation serves as the central engine. Its output is the state vector, or the wave function. Here, the wave function has a single operational purpose. It maps out the exact probability distribution curve for the particle state. Once that distribution is mapped, we use angular brackets to extract statistical averages from the data, which physicists call expectation values. By plugging those expectation values back into our variance equation, we calculate the exact delta terms required by Heisenberg's principle. This statistical engine is not restricted to just position and linear momentum. It calculates the uncertainty for any two classically conjugate variables. By replacing classical Poisson brackets with quantum operators called commutators, the flowchart expands into the generalized uncertainty formula.
This equation dictates that the product of the uncertainties for any two conjugate variables will always be greater than or equal to a specific non-zero constant. The Schrödinger equation operates as a statistical engine. It provides exact mathematical equalities, the probability distributions, to map and explain the inherent inequalities of nature. We can visualize the physical limits of this inequality by returning to this graph mapping the standard deviations of position and momentum. Because the uncertainty principle requires the product of these two variables to be greater than or equal to Planck's constant divided by 2, the minimum possible uncertainty forms a specific curve, a rectangular hyperbola. This curve establishes a hard physical boundary. Any coordinate falling into the area below and to the left of this hyperbola represents a state of precision that physically cannot exist in our universe. While we cannot cross that boundary, modern fields like quantum optics utilize a technological workaround known as squeezed states. Researchers can carefully arrange matter to ride the exact edge of this hyperbola, driving the variance of one variable, like position, incredibly close to zero. However, the mathematical product must remain constant. As you squeeze the variance on the horizontal axis toward zero, the uncertainty of its conjugate variable is forced to skyrocket toward infinity. Nature allows us to optimize certainty, but strictly enforces an exchange rate. Absolute precision in one domain mathematically guarantees absolute ignorance in the other. If this rule applies to everything, we have to ask why we don't observe this hyperbola of uncertainty when throwing a heavy boulder. The boulder moves steadily with no visible fuzziness in its trajectory. The answer lies in the energy scale. Macroscopic objects operate in the realm of joules, while the quantum of action, Planck's constant, is on the order of 10 to the power of negative 34 joules. At the macro scale, Planck's constant is functionally negligible. Classical mechanics is not a separate, independent set of physical laws. It is simply a mathematical approximation of the quantum toolkit. But if we pivot to the opposite extreme, we eventually hit length and timescales so small that our quantum toolkit yields mathematical nonsense. The universe is built on fundamental constants of nature: Newton's gravitational constant, the speed of light, and Max Planck's quantum of action. When you take specific combinations of these constants, you derive the Planck length at 10 to the negative 35 meters and the Planck time at 10 to the negative 42 seconds. Below these thresholds, our mathematical concepts of continuous space and time break down completely. John Wheeler described human knowledge as an island. As our quantum toolkit improves and the island grows, it simultaneously increases the perimeter of our ignorance. The failure of our equations at the Planck scale proves that there are deeper, more fundamental mechanics still waiting to be discovered.